This is Cordant, and Cordant is also an open source technology built and maintained by Mirantis that provides an orchestration layer that ties every single thing together to achieve a single control plane for your entire edge fleet across any infrastructure. Thank you for joining, everyone, wherever you are in this world. Good morning, good afternoon, and good evening. I'm Ionel, and I lead growth marketing here at Mirantis, and I spend a lot of time working directly with infrastructure teams and our customers. So this gives me the opportunity to have a front row seat at a problem that I think many of you may be facing when it comes to deploying Kubernetes at the edge. Today's session, as just mentioned, is talking about Kubernetes at the edge at scale, not the theory of it, but the operational reality of what happens when the cluster count climbs significantly across dozens to hundreds of distributed edge environments, and how to build the proper architecture and operational model to be able to tackle that scale without allowing it to break. We have roughly 45 minutes together today. So the first half of this will be focused on the problem that businesses are facing. And then the second half, I'm going to be able to discuss a little bit about the framework, the stack, the technologies, and the way you should be thinking about this problem at scale. And at the end, we'll take a look at a customer case study of one of ours that has hundreds of different clusters deployed across various different locations. And then I'll open it up for questions. So before jumping into the problem, let's talk about the reality of edge deployments today. Let's start off on the right-hand side of the screen at the top to talk about the cluster count growth that we have seen across various different organizations. In 2023, businesses reported that they had anywhere from 15 to 20 clusters at that time. And what we've seen is a significant increase in cluster deployment across various different edge sites, where it grew roughly 3x. So if you had 15 to 20 clusters back in 2023, fast forward to today, chances are you're managing anywhere from 40, 50, 60, and even more clusters. And unfortunately, the teams that are responsible for managing these clusters generally stay flat. But that's not the significant problem. We will touch on what the real problem is, and generally speaking, it's from an architectural standpoint. Under the 3x is the amount of time the ops team is focused on patching, upgrading, configuring, and overall firefighting versus building. So unfortunately, a lot of their time, due to the cluster growth over time, is focused on, again, patching, upgrading, configuring, and firefighting the hurdles that they may be facing versus actually focusing on building and deploying new clusters at scale. And this results into something that we've seen, which incident resolution per cluster has increased drastically, roughly 3x. And the primary reason to why that has happened is not because the incidents are harder. That sometimes may be the case, but generally is not. But it's actually because of the architectural decisions that have been made, where you can't see what has changed, when it changed, and every incident's troubleshooting starts off as a mystery. And on top of that, what we've seen is roughly 40% of organizations are planning on deploying more than 50 clusters at the edge with no change to the operational model. And that's the thing that's important to sit with. The cluster count is growing, but the approach, the architecture, the team size generally remains the same. And usually that's the gap where the pain truly lives. So let me make that a bit more concrete. Here is a rough case study of a manufacturing company that started off with 8 edge clusters deployed many years ago with 1 ops engineer. Troubleshooting was straightforward, manageable, and identifying cluster drift or configuration drift was normally under control. 8 edge clusters to 1 operations engineer, not too difficult. But the challenge that happened was, as the business grew, more and more clusters were being deployed across various new sites, and that introduced configuration drift. The business went from having 8 clusters to roughly 47, 48 clusters, which is a 6x increase in the number of clusters they were managing, but still only 1 ops engineer. So from what we've seen, this actually isn't necessarily just a staffing problem. It's usually an architectural problem where you cannot hire your way out of this, and instead you need to be able to create some form of standardization across the different clusters that are being deployed anywhere. But what specifically breaks at scale across the edge, and why is it so much more difficult to manage than cloud Kubernetes? Well, there's 4 structural reasons to why edge Kubernetes is fundamentally a different problem than cloud Kubernetes. First, connectivity is generally unreliable. Edge sites lose connectivity, GitOps principles break, and clusters diverge silently. By the time you reconnect those clusters or those environments, you've already accumulated significant drift that you didn't even know what was happening. Which leads me to the second point, which is actually one of the biggest challenges that we've seen with deploying clusters at the edge, which is environments are heterogeneous, meaning they have different hardware architectures across every single site, whether it's x86, ARM, some constrained nodes, and so forth. The challenge there, and we'll go deeper in this, is that every pipeline, every image is deployed slightly differently, creating a non-repeatable environment for deploying applications on top of those edge environments. On top of that, scaling compounds every single one of these elements. 10 clusters at one point with an okay architectural decision is a small problem. 50 clusters with the incorrect framework or architecture becomes a crisis, regardless of the amount of operational folks that you have that can actually firefight some of these things. And if you think about it, every single manual task that you had to do for reconciliation, patching, upgrading, whatever it may be, for 10 clusters, you can perform that in an ad hoc way. But of course, with 50, you're now performing that 50 different times to ensure that those clusters are standardized across the entire fleet. And lastly, we do see that headcount grows linearly at best, while cluster counts are growing exponentially. So there is a ceiling where the current approach simply stops working depending on your architecture, and you usually don't necessarily see what is coming until you've actually got there. So let me take an entire slide to talk through the heterogeneous challenge that we've seen for businesses. And there's 4 failure modes that we see. None of them are theoretical. This is exactly what we see consistently across different customer environments. The first, which is a big one, is configuration drift. Clusters start identical at deployment, but within weeks, they begin to diverge. A patch applied on 30 of the 40 total sites, but not others, meaning there's significant cluster drift, different configurations across the different clusters, and so forth. So when a local engineer specific to that site makes a tweak that solves an immediate problem, generally speaking, this comes significant technical depth because that individual is the primary source of truth when it comes to the change. And that's something that is going to create significant confusion when managing hundreds of different clusters because there's no single source of truth for what any cluster's actual state is. So when an incident hits, you start from zero every single time. The second thing we see is a governance breakdown. Policy defined at the beginning of the cluster deployment slowly erodes. There's role-based access control settings drift from the standard. Audit trails are fragmented across different sites. So when compliance is necessary, it becomes a manual exercise before every single audit. So significant amount of engineers, significant amount of time going cluster by cluster to truly understand the entire audit trail to achieve compliance. The third bullet, operational cost inflation. Every upgrade, every patch is repeated per site. So the on-call burden grows with every single cluster that is added, which creates inconsistent response times. The blast radius is increasing drastically whenever there's new clusters introduced. And your best engineers generally are spending their time, as mentioned, firefighting versus building or deploying a standardized template. And this brings us to the plateau problem. This is one of the problems that surprises most teams. Standard approaches work fine up to about 10 clusters. Beyond that, the complexity compounds significantly and faster than you can manage it. The same the same team with the same tools that were able to confidently manage 10 clusters cannot run 40, 50, 60, hundreds of clusters the same way. So the point I want to get across here is without a new operational model or framework, the growth of the clusters being deployed becomes a significant challenge. There's too much complexity, too little velocity, and it's only getting harder and harder for the team. Now let's talk about the heterogeneity piece, because this is where most teams are surprised by how deep it actually goes. Most folks, when they think about heterogeneous environments, think primarily around hardware diversity. x86 here, ARM there, and that's very real. But it's only the first layer of the problem. There are 4 distinct layers of variation across edge environments, and each and every single one compounds each other. First, the compute architecture. x86 is used at large sites, while ARM may be used at smaller field locations in IoT gateways. Most Kubernetes distributions are going to assume x86, but ARM, as we all know, requires separate image builds, separate pipelines, different testings, which creates an environment where most teams have challenges managing both or maintaining both. And ARM, generally speaking, will be treated as a second-class citizen or skipped entirely. The second point here is infrastructure substrate. Bare metal may be used at high-performance sites, virtual machines where legacy VMware exists, containers on bare metal. Often, this is the environment of multiple different sites for different businesses. This is going to continue to evolve as a significant challenge with AI workloads being introduced. So oftentimes, we see all 3 of these different infrastructure substrates across the same fleet, and the deployments evolve organically over the years. And being able to have a repeatable, standardized, declarative environment is incredibly difficult to introduce when you have this level of complexity. The third is network topology. Generally speaking, these environments are always on at headquarters. And for remote locations, it's more intermediate. Some are air-gapped environments, depending on the industry and the facilities, government, defense, financial, and they still need very high latency that are connected to some satellite locations as well. So GitOps workflows assume the cluster can pull, central control planes assume they can push, but neither of these hold true in these various different environments, which creates another layer of complexity. Lastly, operational context is something that most businesses don't talk about enough. Some sites have local IT folks, some do not. Some sites you can drive to, some you can't. Many have different compliance requirements in different geographical regions and so forth. So creating a standard ops model is the only way to go when it comes to deploying Kubernetes clusters at scale across the different environments. And unfortunately, standard Kubernetes tooling was designed for the cloud, and the cloud has one defining characteristic: uniformity. The assumptions baked into the tooling are structurally false at the edge, and that's not a configuration problem, it's an architectural mismatch. So we have compute architecture, infrastructure substrate, network topology, operational complexity, and every single one of these compounds on top of each other. So that's the full problem picture. But let's discuss the frameworks and the operational architecture that one should use when thinking about how to actually tackle this. So the first part of the session was talking about the problems, specifically to edge environments, the heterogeneous aspect, the compute architectures, the operational burdens, the lack of standardized processes across x86 versus ARM versus different IoT devices. And now we're going to actually take a look at what the proper operational framework looks like to actually be able to tackle this at scale for tens to hundreds of different clusters. So what is the proper framework to actually be able to have a consistent edge operation? We're going to start off directly in the middle. And you heard me use this word a bit. Standardize. Declarative cluster templates as a single source of truth. Every site, regardless of the hardware, regardless of the geography, provisions from the same baseline. The variation that causes drift normally gets eliminated at the source and is not patched after the fact. So this gives you a GitOps native desired state defined in the code. So drift is normally caught automatically and not discovered during an incident. On the right-hand side, we have centralize. And the idea behind centralize is one single control plane that can manage, operate, and deploy clusters across all edge environments and all edge clusters. Not one dashboard per region, not one tool per team, but a unified, centralized control plane, which unifies observability, unifies policy enforcement, unifies the lifecycle management of all of the clusters, and of course, governance is at scale. And lastly, we have automate. The ability to upgrade, patch, configure changes propagated that is entirely done automatically. So the idea is simple. Self-healing clusters with continuous reconciliation. When the desired state changes, the actual state diverges, the system can auto-correct it to ensure that your engineer is not paged at 2 a.m. to actually go and try to solve this problem. So their job shifts from fixing, patching, configuring clusters to just defining the policy necessary. So you standardize once, you centralize your control, and everything else is automated. Now let's discuss the technology layer that actually makes this very real. At Mirantis, we built and maintain a CNCF lightweight Kubernetes distro built purposely for the edge. The foundation that lives on every single edge node is purpose-built for the environment we've described. Single binary, zero external dependencies, not marketing language, but very specific architectural decision, which gives you one binary, which works where other distributions tend to fail because it doesn't assume the infrastructure they assume. So it can be deployed anywhere on any device. And it's incredibly lightweight. So it has a minimal footprint, runs on x86, ARM, some form of constrained bare metal, does not matter. And on top of that, K8s is supported for a fully offline installation or air-gapped environment. And as mentioned, it is a CNCF certified Kubernetes distro with zero lock-in, fully open source, and the ability for anybody to take this distro and deploy it anywhere. So let's take a look at what this actually means in detail. And I want to make this clear. K8s doesn't make heterogeneity disappear. It makes it irrelevant to your operational model. Here's the mechanism that we see. K8s ships as a single self-contained binary with embedded components like containerd, kubeproxy, core DNS, all bundled in. There's no package manager, no dependencies necessary, and zero external service assumptions. The same binary runs on x86 server in a Frankfurt data center, can also run on an ARM device in Malaysia. You do not maintain two different pipelines, no separate image registry, and no architectural specific runbooks. So it's one template, one binary across any hardware with the same deployment command and the same result. So your ops team doesn't even need to know what the architecture is underneath. They apply the template, K8s handles the rest. The template is the template everywhere, regardless of the site and regardless of the hardware that it's running on top of. This is Cordon, and Cordon is also an open source technology built and maintained by Mirantis that provides an orchestration layer that ties every single thing together to achieve a single control plane for your entire edge fleet across any infrastructure. On the left-hand side, you can see your custom infrastructure, whether it's in a data center, whether it's at the edge, which is what we're focusing on today, and any infrastructure, compute, network, GPUs, DPUs, TPUs, or whatever it may be, it can run on top of. And through Cordant and creating a centralized control plane that actually allows you to manage, monitor, deploy standardized declarative templates or K0s clusters across any infrastructure, you achieve very specific customer outcomes. And the point I want to make here is the ability to achieve standardized templates across any Kubernetes cluster with the ability to have self-healing, self-updating, self-upgrading without ever being impacted by some form of configuration drift. So this is the full ecosystem picture. You can see highlighted in red is the edge, and above that is going to be the Kubernetes at the base layer or the runtime that you're using. We talked about K0s today, which is a lightweight Kubernetes distro, but there's plenty of lightweight Kubernetes distros available that is fully open source for businesses to use. On top of the underlying Kubernetes distro, we provide Cordant. And Cordant has three core components that truly take your infrastructure to the next level. First, we have KCM, or Cordant Cluster Management, which is the ability to provision and manage the entire lifecycle of those Kubernetes clusters. We have Cordant State Management, which ensures that you have the correct state for policies, resources, and so forth. Then we have Cordant Observability and FinOps, which is going to give you the full observability, logging, monitoring, and cost optimization. Those are the three components that make Cordant what it is today. It's centralized control plane for your entire infrastructure from metal all the way to model, depending on if you're deploying LLMs. So let's take a look at the Cordant components in detail. As mentioned, there's three integrated systems, and each and every single one of these answers a different operational burden or question. On the left-hand side, we have Cordant Cluster Management, which is simple as in what is a cluster. So KCM provisions and manages Kubernetes clusters. The lifecycle of these clusters via CAPI, right? Cluster API. It handles cluster creation, upgrades, versioning using specific cluster templates that are declarative, version control definitions that deploy consistently across your entire infrastructure and whatever is underneath. This is a very important point when it comes to standardizing your Kubernetes clusters. In the middle, we have KSM, Cordant State Management, which should be thought of as what runs on the cluster. So KSM manages the deployment and the lifecycle of applications and services running across the cluster using service templates. They're Helm-like, but they can be deployed fleet-wide across all of your different clusters. And this operates independently of the cluster setup, so application delivery is decoupled from the infrastructure lifecycle, which is very important as well. And the third, Cordant Observability and FinOps, or COF, which is the tooling that allows you to aggregate your metrics, your logs, your traces from all managed clusters into a single pane of glass across the entire fleet, feeding data into the alerting, visualization, cost optimization, and so forth across different tenants and clusters. So 3 systems, 3 operational challenges or questions it solves, 1 centralized control plane. Now, let me show you the mechanism that makes all of this work at 2 a.m. when you're not watching. So how does Cordant and K0s keep 100 clusters in check? This is the reconciliation loop. The mechanism behind every claim about scaling without growing your team is done here. First, in the middle, we detect. Cordant continuously compares actual state against the desired state for every single cluster in the fleet. And that is done on a configurable interval, constantly, not just on the events. So when an actual state diverges, the drift is categorized, configuration mutation, missing component, version mismatch, policy violation, and each category has a known remediation plan. On the third, or on the second, on the far right, is remediate. For drift with a safe deterministic remediation path. If somebody deletes a config, a change to role-based access control, some form of binding, a missing operator, Cordant corrects it automatically. No ticket, no page, nobody is pinged at 2 a.m. Every remediation is logged with a timestamp, the cluster identity, the delta, the action that was taken. This is the entire log for your compliance evidence that we discussed earlier, and is generated as a side effect of normal operations, ensuring you are always operating in a standardized format. And on the far left, there's service exceptions. So for drift that's ambiguous or high risk, Cordant is going to surface this to your engineer with the full context. What changed, which cluster, the recommendation to fix it, and the engineer either approves or overrides that decision because they're reviewing a very clear, specific exception and not debugging this from scratch. So here's what it looks like in practice at 2:03 in the morning. A network policy is modified on the cluster site at site number 34. Cordant may detect that, categorize it as a safe remediation, so it's eligible to make the change. It restores the policy automatically. The event is logged, and when your team logs in to see what's going on, they can investigate this entirely on their own and see what actually took place and what changes were made. So the key shift that businesses see is you're going from fixing clusters to defining policy. So instead of having fire drills to fix a specific cluster, you have a defined policy that you work through to actually solve the given problem and create a standardized template. So here's a day in the life for somebody that's operating edge clusters without a solid framework or architecture. 4 different scenarios. This is a day in the life of a team running 40 edge clusters without a proper framework. On the left, there's an incident at site 12. The alert fires, the cluster is unhealthy, the engineer has the SSH in, the config looks different from site 8 to site 3. There's no audit trail, there's no record of what took place, who changed it, and all of the engineers are pulled in to actually figure out what is happening, and it takes them hours and hours to solve a simple mystery. The second one could be a quarterly upgrade cycle where the team needs to actually upgrade every single Kubernetes cluster because Kubernetes upgrade is needed, right? And they got to repeat this for every single cluster at every single site, and this takes weeks on weeks to achieve across so many different clusters. Then there's compliance and new site onboarding, which I think is quite self-explanatory. But with the proper architectural framework, the 4 incidents are a completely different story. For incident at site number 12, the alert fires. Cordant detects the drift from the desired state. It identifies the root cause for visibility immediately in the centralized dashboard. It can auto fix it if the correct permissions are introduced. So the cluster is reconciled to a known good state, and one engineer resolves all of this in 10 minutes versus spending hours on trying to debug and understand where something took place. For the quarterly upgrade cycle, this one is quite simple. Push a template change to Git, done. Cordant propagates the upgrade to all 40 clusters automatically simultaneously. Some exceptions may be surfaced. The engineers may review the 3 different sites, and some may need attention and some may not. But the point I'm making here is you're able to upgrade all of the clusters simultaneously from one another automatically without having to go through this one by one. So what does this framework actually deliver? Everything we've discussed so far, the framework, the stack, the reconciliation loop, this is what it looks like in production at a major financial institution. The challenge that they faced was eliminating configuration drift across 50 plus Kubernetes clusters and to improve auditability for the particular regulatory compliances that they need. So the task that was put in front of them is architect and operate a fully declarative GitOps native platform, integrating KCM, Keros, and K0s for a fully contained Kubernetes distro. And this speaks directly to every single challenge we discussed today. This created a uniform policy for more than 50 clusters across VMware and cloud environments, and was able to solve the heterogeneity problem, different infrastructure, different substrates, different hardware, all solved through a template-driven audit. So the customer went from days to minutes on cluster provisioning, and the same new site onboarding process that used to take days to achieve took minutes. And this is not because the team grew, but instead because the template does the work. And all 100% of clusters are approved with very specific compliance policies. So compliance remains always on. Same team, same infrastructure, different operational model. That's the entire argument. It's so important to define and architect the correct architecture for your specific needs. Thank you, everyone. I hope this was informative and helpful. I can't thank you all enough for taking time out of your day to meet with me, whether it's in the morning, the evening, or the afternoon.